got a question for you. If I was to take this ordinary piece of paper and tear it roughly in half, and then stack it like that, and then take my stack and tear it and stack it, and so I've done it twice. I've torn it and stacked it twice, and I'm going to tear the stack again. That's 3 times. Stacked it again. I'm going to do it again 4 times. It's getting a little tough to do now. Stack it. If I was to do that 50 times, tear the stack and stack it again 50 times, how tall do you think, how high up do you think this stack of paper would be? Like if I put it on the ground, how high above the ground would it go? Pause the video and take a guess. What do you think? There's clearly a mathematical relationship between the number of times I tear the paper and the number of pieces of paper that there are. So let's see if we can come up with a model for this. I'm going to label my x and y axes. X we're going to label as the number of tears. It's tears, not tears. There's no crying in math. Y will be the number of pieces of paper. And we'll see if we can come up with a function that models this relationship. So let's make a table. And let's just see if we can figure out the pattern here. So before we tore it at all, we started out with how many pieces of paper? 1. Then after we tore it 1 time, we had 2 pieces of paper. After we tore it twice, we had how many? 4. After we tore it 3 times, we had, this is the thing, it's 8 pieces of paper, right? Some people think it's 6, but we're not adding by 2 each time, we're multiplying by 2. The number of pieces of paper doubles every time. And then after we tear it 4 times, we have 16 pieces of paper. 5 times, 32. We just keep multiplying by 2 each time, right? After we tear it 6 times, we have 64. Whoops. And then after 7 times, that'd be 128. 8 times would be 256. And then 9 times would be what? 512. And 10 times would be 1024. Now you might, at this point, if we just stop, we said we're going to tear it 50 times, but if we just stop here, what do you all think? Does it seem like these numbers are getting a bit bigger than maybe we would have expected at first? If you actually paused the video and made a guess, I'm guessing that you predicted something not super big as far as the height of the stack. But already, after only tearing it 10 times, we're up to over 1,000 pieces of paper. Now, this is a little bit surprising. So now we can see what's happening is if we tear it again, after 11 tears, we'll be over 2,000 pieces of paper. And then after 12 tears, we'll have over 4,000 pieces of paper and so on. So instead of continuing this on by hand, that's going to take a while, I wonder if we can come up with a quicker way to do it. Well, what do you call it in math when you repeatedly multiply by the same thing? When you multiply over and over by the same thing? That's called an exponent, right? So what are we multiplying by over and over and over again? We're multiplying by the number 2. Because every time you tear it, you're doubling the number of pieces of paper. So all we have to do is this. Take the number 2, and it's going to be 2 to the power of what? How many times are we multiplying by 2? Well, we're multiplying by 2 50 times. So if we type 2 to the power of 50, that's going to give us this gigantic number. Remember we talked before about scientific notation? Well, this means that you take the decimal point and move it 15 times to the right. So it's 1 with 15 zeros after it, basically, right? That's an enormous number. It's an astronomical number, a number that we can't even conceive of, right? But you say, okay, well, but paper is super thin. So if you were to Google how thick is a typical sheet of paper, you'd come up with 0.004 inches, right? So what we can do is multiply this by 0.004, and that gives you 4.5 trillion inches. I think that's what that is. Do we have any idea how high that is? I mean, An inch isn't super big, but that's a lot of inches. How high is that anyway? Well, let's convert into units that are a little bit easier to understand. So let's go from inches to feet. So there's 12 inches per foot. So if we just divide this number by 12, then now we're at 375 billion feet. That seems really, really high. Let's convert that into something a little bit more understandable. Let's go from feet to miles. There's 5,280 feet in each mile. So we'll divide by the 5,280. And we're left with this number, which is 71 million miles. 71 million miles. If you were to look up that number goes almost to Mars, depending on depending on where the orbits align. Way past the moon. This stack of paper would go way, way, way out into space. If you think that's a mistake, I mean, I'm going to go out there on a limb and guess that if you pause the video, you predicted maybe like 4 inches or maybe a foot or something like that. But the answer is actually 71 million miles. How is that possible? Did we make some kind of mistake? To get some kind of an idea of what in the world's going on here, it might be easier to think about this by making an actual function. So let's think about it like this. Instead of doing 2 to the power of 50, let's do 2 to the power of x, where x represents, we'll do y equals 2 to the power of x. X represents the number of times we've torn the paper. Y represents the number of pieces of paper that we have. Now we can turn this into a table by clicking on the edit list button, this little gear right here. And here is the table that we just sort of started making before. The negative numbers don't really make sense in this context, so I'll get rid of them. Now, all I gotta do is just, instead of manually calculating this, I can just click here in the X column and just press the enter button, and it's gonna automatically give me the next value. So when we tear it 3 times, there's 8 pieces of paper, 4 times, there's 16, 5 is 32. Now I can just keep hitting enter here, and there we are, we've done the first 10. Now, remember we said before with Desmos, anytime you make a table, you can click on this little magnifying glass and it will automatically zoom in on the data, right? So let's do that. And notice what the graph looks like. What we have at the beginning is very small growth, right? It's barely moving up at all. And that's what you saw when I was on the camera before tearing the paper. You saw we had 1 piece, then we had 2, then we had 4. It's not going up by a lot, right? But you can see that what happens is as you keep going further and further and further along, once you start to get a decent sized stack and then you double it, you get an even bigger size stack. Like once you get to 500 and you double it, now you're at 1,000. And then let's keep going. You double 1,000, now you're at 2,000. And then 4,000, and then 8,000, and then 16, and so on, right? And before you know it, by the time we've done it 20 times, we're already over 1 million stacks of paper. If I zoom it out and look at it, you can see again that the growth at the very beginning is super small. But as we go along, the growth gets huge really quickly, right? And so if we go all the way to 50, it's going to be absolutely enormous by the time we get to the end. When you repeatedly multiply by the same thing, that's called exponential growth. Exponential growth is a kind of growth where it grows slowly at the beginning, but then very, very quickly at the end. Exponential growth is extremely counterintuitive to us because in our everyday experience, it often doesn't feel like that's how things work, right? You know, you push on a swing set and the child goes you push a little bit harder, the child goes a little bit further, right? You push the gas pedal a little bit more and your car goes a little bit faster. We're not used to this kind of growth where you tear a piece of paper one extra time and it grows astronomically. That's not the sort of thing we normally experience. And so it's very counterintuitive. We're used to thinking in sort of a linear growth model, not exponential growth. You might be thinking, well, but this is kind of silly. I mean, who even cares about tearing a piece of paper? You can't, it's not even a real thing. Could you actually do that physically? Well, the thing is, exponential growth is a hugely significant part of the real world in which we live. Let me give you a few examples. Population growth. You have a few people. Let's say you're starting a colony somewhere. You have a few people, and let's say each couple has 3 children on average. Each of those children has 3 children. Each of them has 3 children. What are you doing? You're multiplying repeatedly by 3. The population grows slowly at the beginning, but quickly, uh, very fast later on. Um, this is how epidemics spread as well, right? You got patient zero. Let's say patient zero infects 4 other people. Each of those 4 people infects 4 other people, and so on and so forth. You keep repeatedly multiplying by 4. Before you know it, millions of people have been infected by the illness. Now, exponential growth really, really brings glory to God, because think about this: there are tons of things in the physical universe that work like this, where you have take for example proteins, which are the building blocks of life, right? You have to string together a string of a large number of amino acids in just exactly the right order in order to create a functional protein. Well, think about it. Every time you add a new amino acid to the chain, there are a lot of ways to do it wrong, and only one way to do it right. And so every time you string together a new one, the number of wrong ways that it could happen where it would not be functional is multiplied every single time. And so by the time you get to the end of the chain of 150, let's say, amino acids, it's been calculated that the odds of uh, creating a functional protein, there's more wrong ways to do it than there are atoms in the entire physical universe. It's astronomical. It's amazing the utter precision that God uses in all the things that He does in His physical universe. Or let me just give you one more example that maybe brings it a little bit closer to home. Think about the events that had to take place for your parents to get together so that you would be born and you would be alive right now. The number of events that had to take place, the number of ways for each of those events that it could have not happened. Every time all those events are strung together and they multiply together, it's literally astronomical. The chances of you being in existence, God had to work everything out just exactly right to bring you into existence and to give you life. And the same thing holds for all of His purposes. Think about the number of events that had to take place, the number of ways that it could have gone wrong for Jesus to not end up at the cross to die for our sins. God's ordering of history is with absolute precision. You probably heard the financial advice that if a person starts investing money earlier than someone else, then the person that invests later, it's almost impossible for them to catch up. Well, here's a graphical illustration of that. The reason for that is because of exponential growth. Think about it like this. When you invest money into an account, you're getting interest on it, right? So what we have here is 3 different people that all invest the same amount, $1,000 into the account. And they all have the exact same interest rate, 5%. So at the end of the compound period, you've got your $1,000 in the account, and you get the 5% interest added into your account as well. So now you have a little bit more than $1,000 in your account. And so then the next time that it's compounded, you're getting interest on your interest. So you get a little bit of extra interest into the account. And so you see it's going to slowly, only growing slowly at the beginning, right? But the longer you keep your money in the account, that interest starts to accumulate into your account. And so now you're getting interest on an even bigger amount and on an even bigger amount. And over the long haul, way down in the future, you're going to start to see exponential growth on your investment. And so what we see here is these 3 guys that all invested the $1,000 into the same account with the same interest rate. The difference is the purple person here, they invested when they were 25 years old. The green person invested when they were 35, and the red person when they were 45. So there's a 10-year gap between each of them. And you see at the beginning, the gap is not super big, but notice as the years roll on, the gap widens between them, right? You can see that it's getting bigger and bigger, and that's because of the exponential growth. Exponential growth means that it's going to grow slowly at the beginning, but fast later on. Similarly, exponential growth has a lot to tell us about buying a house. I looked up the median house price in the area where I live, which is in Greene County, Virginia, and it's currently $438,000, and the interest rate is just about 7% right now. And so what we have here is the x-axis represents the number of years that you've been paying off your house, and the y-axis represents the amount of money you owe on your mortgage. So let's suppose that somebody takes out a 30-year mortgage and they take out a $438,000 mortgage. You can see that the x-axis represents that after 30 years you owe nothing. You've finally paid it off. It's a 30-year mortgage. Now here's the amazing thing. What this is calculating is the amount of money you're paying per month, $2,900. This is the total amount that you end up paying over the course of 30 years. That's over $1 million. The house was $438,000. You're paying more than double of what it was worth. And that extra money is all interest. You can see here that in total, after the 30 years, you will have paid the bank $611,000 in interest. And why is that? Well, look at the beginning here. Look at the way this graph works. When you're paying it off month by month, you're paying your $2,900. The amount you owe the bank is only going down slowly at the beginning. That's because you're paying almost all interest at the beginning. 7% interest on $438,000 is a huge number. So you owe a ton of interest at the beginning. So every month when you pay your $2,900 to the bank, you're only the amount you're owing them is only going down slowly. But by the end, once you've paid off a lot of your mortgage, then 7% on a small number is not very much. So by the end, you're paying it off fast. So this is another example of exponential growth, where it's dropping slowly at the beginning here and then quickly at the end. So one strategy, if you could swing it, that would help you out a lot, is if you could pay this off faster. So if we pay this off in 15 years, let's say, instead of in 30, you can benefit more from the rapid growth at the end. You're cutting off the part at the beginning where you're paying almost all interest. Even though you have to pay an extra $1,000 per month, notice the total amount you end up paying is only $708,000. You're only paying $270,000 in interest instead of $611,000. Exponential growth happens whenever you repeatedly multiply by the same thing. It grows slowly and then quickly. Slowly at the beginning, quickly later on. But something else can happen. You could have a situation that's called exponential decay. And that looks like this red graph over here. What would happen if we multiplied over and over again by 0.5 or 1/2? Well, imagine you start with the number 1,000, let's say, for example. Okay, you multiply 1,000 by 1/2, and now you have 500. Now you multiply again by 1/2, now you have 250. If you multiply 250 by 1/2, then you have 125, and so on. And so what happens with multiplying by 1/2 over and over again is it's going to drop quickly at the beginning, and then it's going to drop slowly at the end. This is what we mean by exponential decay. So if you multiply over and over again by 3, it's going to grow slowly and then quickly. If you multiply over and over again by 1/2, it's going to drop quickly and then slowly. Well, how would you know from just looking at the equation that this one would be growth and this one would be decay? How could you tell? Well, it all has to do with the base. The base is the number that you're multiplying repeatedly by. So let's look at some examples here. Suppose you have a base of 2. That's going to be exponential growth, because if you keep multiplying by 2, it's going to get bigger slowly at the beginning, fast at the end. That's like what we did with the paper tearing problem. If I make this base bigger than 2, it's going like 2.17, let's say, it's going to grow even faster. The bigger the base, the faster it grows. That makes sense. If I make the base smaller, it's going to grow more slowly, right? So if I drop below 2, it's going to keep growing, but more slowly. What happens as the base approaches the number 1? What happens if the base gets to 1? Well, notice when the base is exactly 1, we have a flat constant. That's because when you keep multiplying by 1 over and over again, it stays the same, right? Well, what happens if we keep going a bit further past 1? Now, it's actually dropping. And that's because when you're multiplying by a number like 1/2, you're cutting something in half. It's actually getting smaller. It's dropping, right? So what's the difference between growth and decay? If the base is bigger than 1, it's going to grow. If the base is smaller than 1, it's going to be decay.